Welcome back to SKD's Note. So today we are going to discuss about some DC machines. In the DC machines, in previous class we left at relationship between input power and output power of a DC generator, correct? So let us discuss now. So before moving on to that, you should know that DC machine is nothing but synchronous machine plus commutator, correct? As I said, DC machine is equals to what? Synchronous machine plus commutator. You should remember this, okay? So likewise, DC generator will be what? Synchronous generator plus commutator, correct? Likewise, what we have for DC motor, it will be synchronous motor plus commutator. So here commutator is acting like a converter. Yes, correct? In commutator, in DC generator, how the commutator is acting? It is converting AC into DC. Whereas in DC motor, how it is acting? The commutator acting like inverter, it is converting DC into AC, correct? So you should remember this. Here if we talk about a relationship between input power and output power of DC generator, we have relationship between what? Input power and output power, correct? So if we consider input power is what? Mechanical power input of generator. So you require prime mover to rotate the armature, correct? So that armature is connected to the same shaft of the prime mover, so that as prime mover rotates, it will rotate and there will be a generation of what? EMF, correct? So mechanical power will be equals to what? So TPM. What is TPM? Prime mover torque. TPM means what? Prime mover torque. So then what we have next? Into omega. What is this? Velocity. Then what we have? Power output of generator. What is the power output of generator? That is electrical power is equals to electromagnetic torque into omega, that will be Eg times Ia. Therefore electrical power in a DC generator will be Eg times Ia, and the unit will be in watts, correct? This is electrical power, not the generated EMF, okay? So we have another torque. So in generating action there will be a motoring action taking place, as well as in motor there will be a generating action taking place. So here in generator we call it as a braking torque. Okay, that is due to what? Magnetic drag. So this will be what? TEM, braking torque or electromagnetic torque, will be equals to PE divided by omega. So Eg into Ia by omega will become electromagnetic torque of a DC generator. So in DC generator also, as I said, motor action takes place. The electromagnetic torque, what is TEM? Electromagnetic torque, correct? So this electromagnetic torque due to motor action always acts in opposite direction to the prime mover torque. Okay, so if TEM will be in this direction, TPM will be, that is prime mover torque, will be in opposite direction. So opposite to what? TPM, understood? And therefore this torque is called braking torque. Electromagnetic torque is also called as what? This is also called as magnetic drag. Understood? How the relationship between input and output power of a DC generator. Okay, this is DC generator, don't get confused. Understood? So now let us discuss about DC motor. So what does this DC motor do? So we'll see the two cases here. DC motor with slip rings. Okay, so we have magnetic poles north and south, correct? Then we have a armature, and we have a armature conductors. Understood? So this is how you need to draw. This is what? Commutator, right? This is connected here and this is connected here. This is brush B1 and this is brush B2. Okay, so the circuit is connected like this. When DC voltage is given, okay, this is positive always and this is negative. Here current goes in and here current goes out. So it will be like this, and it's going in, it's coming out. These are what? Flux lines. Understood? So this will be A, B, C, D. So from this figure the current direction is from A to B, correct? And from C to D. Therefore electromagnetic torque is in anti-clockwise direction. So TEM will be in anti-clockwise direction. Okay, and after half rotation CD comes under north pole. Okay, this CD will come like this. It will be CD, then it will be BA, understood? So here this will be north pole and this will be south pole after half rotation. So at that time CD comes under north pole and AB comes under south pole. Here polarity of B1 is positive, B1, here B2, this is positive, and B2 is negative. Hence current direction is from A to B under south pole, A to B under south pole. Okay, this is south pole, right? I have written here. So, and C to D under north pole, therefore electromagnetic torque is in clockwise direction. So what you can say, after every off rotation electromagnetic torque direction is changing, correct? First it will be for off rotation anti-clockwise, then next off rotation it will be clockwise direction. Understood? For one complete rotation the average torque is 0, correct? Anti-clockwise, clockwise. So net torque or average torque is 0, therefore DC supply by using slip rings, motor does not rotate. Tm or average torque is 0, motor will not rotate. Understood? So now with slip rings, the brushes B1 is always, we are talking about slip rings, correct? So the brush B1 is always in contact with conductor AB, and the brush B2, this brush B2 is always in contact with CD. The current in the conductor AB is always cross, whether it exists under north pole or south pole. Therefore the average torque is 0. So for the production of unidirectional torque, current must cross the north pole. Okay, the current must be cross under north pole and dot, see, cross under north pole, dot under south pole. If it is cross, current is going inwards. If it is dot, the current is coming outwards. So here, that is the direction of current should be reversed for every off rotation, means the current should be AC in armature conductor. That means we have armature conductor should be AC. Armature conductor, or what it is also called as what, coil. See sir, this is what your armature looks like. The coil is going like this. Okay, I am just showing you an example. So this is how it has been there. Understood? So I have drawn only one. So here what happens, every half rotation the direction of current should be reversed for every half rotation, means current should be AC in the armature conductor. This can be implemented by only replacing slip rings with what, split rings. Okay, or the commutator segment. Here this is what, commutator segment. This should be removed with the help of split rings. Okay, so with the help of split rings what happens, the current directions is from A to B and from C to D. Therefore electromagnetic torque is anti-clockwise direction as shown. Okay, let me draw it first. This is north pole, this is south pole, and this is what, your armature, and you have armature conductor or a coil. Okay, so this is what mica insulation, you have brushes. Okay, and you will be given a voltage. This is B1 and this will be B2. These are what, magnetic lines flowing from north to south. Okay, so the current direction is from A to B and C to D, therefore torque is in anti-clockwise direction as shown in figure. Okay, this will be cross and this will be dot, current going inwards and coming outwards. Okay, this is what split, you are splitting rings. So after half rotation, CD comes under what? Let me write it here, A, B, C, D. Okay, CD comes under what pole? North pole, and AB under south pole. Now the direction of current is from B to A under south pole. Let me draw it here again. I'll just draw a coil. Okay, so this is north and this is south. Okay, what is happening here? So after half rotation, CD comes under north pole, it is coming under north pole, CD, and BA under south pole, correct? So and D to C under north pole, D to C under north pole. Therefore electromagnetic torque is in anti-clockwise direction because we are splitting phases, correct? So here after half rotation we are changing the direction of current, so hence the torque is unidirectional torque with the help of split rings. Now commutator converts DC supply in the supply terminals to AC in the armature conductors. Okay, what is happening here? So now commutator DC supply is converting into, let me write it clearly, commutator converts DC in the supply, this is what supply, okay, terminals to the AC in the armature conductor. Okay, so therefore the commutator behaves as a mechanical rotating inverter. So this commutator behaves as a what? Mechanical rotating inverter because it is converting DC into AC, correct? Inverter means what? DC to AC. Supply terminal is DC, correct? What supply we are giving to DC motor? AC, DC supply. So in armature conductor they should get what? AC, because it will be rotating, and we need to change the current direction after half rotation to get a average torque of a some value. If the average torque value is 0, then there is no motor and their motor does not rotate. Understood? So here, and the frequency of armature current IA frequency will be what? F will be Pn times Pn divided by 120 and hertz. This is the frequency of a armature current in the armature conductor or a coil. So with commutator segment, the brush B1 is always in contact with the conductor what? So with the commutator segment, the brush B1 is always in contact with the conductor which exists under north pole, and at the same time the B2 will be always in contact with the conductor which is existing under south pole. The brushes B1 is positive polarity, okay, and the brush B2 will be negative polarity. So it maintains cross in the conductor under north pole, correct, cross, dot under south pole. Therefore, AC supply in armature conductors and torque is unidirectional torque. Okay. So let us discuss about now back EMF. What is back EMF? See sir, back EMF is means what? In DC motor also generator action takes place. In DC motor also generator action takes place. Correct. So due to generating action, the rotating conductors, due to generating action, what happens? Rotating conductors, that is rotating armature, rotating conductors is nothing but what? Armature conductors cut the flux. Correct. So due to and an EMF is induced. This EMF is called what? Back EMF. It always opposes the supply voltage. EB opposes supply voltage. So back EMF opposition can be represented in terms of mechanical power developed. Opposition can be represented as mechanical power developed. EB into IA, mechanical power developed. Okay. So applying Fleming's left hand rule. Okay. By applying Fleming's right hand rule to find the direction of current, then we can get dot under north pole, cross under south pole. So in this case it is reversing, that is opposite direction of current is passing in the armature winding. Opposing direction of current is passing in armature winding. Understood? So if this happens in DC motor, E will be equals to EB plus IA RA. What is this V? Supply voltage. In every motor there will be a generating action. Due to that generating action, armature conductor cuts the flux, and due to that flux cutting there will be a EMF. That EMF is small amount, that EMF is called as back EMF. Understood? What is EB? Back EMF. So let us see the circuit model. Okay. or let us see the first generating mode. Generating mode. What is generating mode? So if we talk about generating mode for DC generator, shaft power input, okay, for DC generator, shaft power input will be equals to what? Eg into Ia plus no load rotational loss. Understood? So and Vt will be equals to what? Vt will be the terminal voltage, and Vt will be equals to Eg minus Ia Ra. So where Vt is what here, sir? Armature terminal voltage. Armature terminal voltage, okay. So Ia is what, sir? Here Ia is nothing but armature current. Ra is what, sir? Ra is nothing but armature resistance. And while considering brush contact drop is usually taken as a constant at 1 or 2 volts. This drop is independent of armature current, okay. We will also consider brush voltage drop, okay. It will be around 1 to 2 volts brush voltage drop, okay. So therefore Vt will be Eg minus Ia Ra minus 2. Okay. So here multiply Ia on both sides, you will get Vt Ia equals to Eg Ia minus Ia square Ra minus 2 times Ia, or electrical power output. Okay, let me write it here. Okay, let me write it here only. So we can write it as electrical power output will be equals to electromagnetic power electromagnetic power minus ohmic losses, I square R losses, minus brush contact drop losses, which we have seen, correct? So if we consider, okay, so you will be having a Ra, and this is a setup of DC generator or DC machine. So here DC generator, with the help of prime mover we are running, okay. So this will be your N, and this is your electromagnetic torque, and this is shaft power or input power. So here across generator will get Eg. This is what the terminal voltage Vt. Then you will be getting out a armature current. This is armature resistance. So here this is what field resistance. So this is what field current, plus and minus. You will be getting a field voltage. It might prime mover might be watts, or it might be a diesel generator, okay, or any other aspect. So this is for DC generator. DC generator. So if we draw for DC motor, this is what armature resistance, then you have a motor here, correct? You have terminal voltage, Ia is coming in current, you can call it as Vs also, supply voltage. You will be getting a back EMF as usual, as we discussed. So here electromagnetic torque and the speed will be in same direction. You are getting shaft output power. So mechanical work is done here, okay. So you will be having field windings here. This is resistance field winding, and for that you are giving a field applied voltage, the DC format, and you are getting field current, okay. So here this is in generating mode, okay, generating mode. This is in motoring mode. So we have discussed in generating mode, correct? So let us discuss about motoring mode. So in motoring mode, here also for a DC motor, shaft power output for DC motor, shaft power output, this is the shortcut for output, okay. So EB into IA minus no load rotational loss, okay. Again we are getting the same thing. So and Vt, consider it as EB plus IA RA plus 2 multiply Ia on both sides. What you will get, sir? Vt into Ia equals to EB Ia plus Ia square Ra, it will become ohmic losses, and 2 times Ia. So it will become electrical power input equals to electromagnetic power plus ohmic losses. Correct, here we are saying ohmic losses. Then you will get what? Plus brush contact losses. Understood? So in DC motor, Vt will be Eb plus IaRa. Correct? So we will be getting as input power equals to what? Mechanical power plus I square R. From this equation you can get this, call this as 1 and 2. From 2 we will get this. Okay, input power equals to mechanical power plus I square R. So mechanical power will be Eb times Ia. So this Eb times Ia is what? Electromagnetic torque into velocity, angular velocity. Then TEM, electromagnetic torque, will be mechanical power divided by angular velocity. So it will become Eb times Ia divided by omega. So the induced back EMF, or the back EMF induced in AC is AC, correct? In armature winding, the back EMF induced in the armature winding is AC, and the frequency, as we discussed, what? F is equals to Pn by 120 Hz, but with respect to the brushes, back EMF is DC. Okay, understood? So assumptions to find the direction of induced EMF in the armature winding is what? So armature rotates in anti-clockwise direction, but poles are rotating in clockwise direction. You should remember that. See, in order to find the direction of induced EMF, you should remember that the poles, these are rotating in clockwise direction. Let me draw it separately. Okay, and the armature in between them is rotating in anti-clockwise direction. Understood? So armature rotates in the counterclockwise direction. Okay, counterclockwise direction. This is what? Armature. This is what? Poles. I am drawing it separately in order to understand you. So armature rotates in counterclockwise direction, but poles are MMF in opposite direction. That's it. You should remember this. Assumptions to find the direction of induced EMF. Let me draw a clear one. Here you will get to know what it is means. So you have this. Okay, so you have this, correct? Then you will be having north pole here and the south pole here. Okay, north and south, cross and dot. Okay, if we have an axis here, this is rotating in counterclockwise direction. What it is? Armature core, armature. Okay, this way it is rotating in clockwise direction. What it is? The rotation of magnetic poles is rotating in what? Clockwise direction, and it repeats. So construction details and all we'll see in the next class. Okay, thank you for watching the video. If you like this video, please share with your friends and subscribe to the channel. Mention your suggestions in comment box. Thank you for watching.